then I think that Fernando will talk about the third. So, okay, so just for people who missed Lance's talk, Lance gave a nice introduction about these dual conformal structures. So it started with work of Alday and Maldacena last year, who used the invariance of the ADS 5 times S5 metric under just the usual T-duality, bosonic T-duality, to relate planar super-Yang Mills amplitudes and Wilson line correlation function as strong Tooth coupling. So it was strong Tooth coupling they had to use because if you look at how the ADS5 metric transforms, so it's just a standard T-duality where the term in front of dx squared gets inverted, then you find that the ADS 5 times S5 metric is invariant, at least after doing this redefinition of y. But the Ramon-Ramon field strength is not invariant, and also the dilaton is not invariant. Now these changes of the Ramon-Ramon field strength and of the dilaton are lower order in the ADS radius. So at least if one is looking at strong Tooth coupling or large radius, one can ignore these effects. But a little bit later, this group of people just did perturbative computations of n equals 4, d equals 4 super-Yang Mills amplitude, so planar n equals 4, d equals 4 super-Yang Mills amplitude, and also found a relation to these Wilson line correlation functions. But this was, of course, at weak Tooth coupling because they were doing perturbative computation. So the obvious question is if this Maldacena result can somehow be extended to describe planar super-Yang Mills amplitudes at arbitrary Tooth. Thanks. Okay, so the summary of the talk is essentially on this slide. So the idea is that you have both bosonic and fermionic T-dualities. And so I will, of course, explain what are fermionic T-dualities. And by including both of them, you can show that not only ADS5 metric is invariant, but the full ADS5 times S5 background is invariant. Okay, so this fermionic T-duality is just a straightforward generalization of bosonic T-duality. It's kind of shocking that nobody has studied this before, but it's just you have this, you need a fermionic isometry, which like, if you want to just study bosonic isometries, if you just have one, it's automatically abelian, but for fermionic isometries, the square is not necessarily 0. So you need an abelian fermionic isometry, and then you find there's a natural generalization of this Busher procedure for describing bosonic T-duality to fermionic T-duality. So fermionic T-duality will turn out to leave the metric and the B field invariant, but it will transform the Ramon-Ramon field strength and the dilaton. And if you choose the bosonic and fermionic T-dualities in a certain way, so you choose the bosonic T-dualities in the same way as Alday and Maldacena did, you bosonize the 4x variables of D Swarm-Minkowski space, and you choose 8 chiral theta variables, and you T-dualize those, you find that the complete background is invariant. So the transformation of the Ramon-Ramon field strength and dilaton from the fermionic T-duality exactly cancels the transformation from the bosonic T-duality. Okay, so if one ignores the issue of polarization dependence, so we still don't understand how to describe polarization dependence in the Wilson line description, this at least explains why the two should be related at arbitrary Tooth coupling and not just at strong Tooth coupling. Okay, so there are probably other applications of this fermionic T-duality. So one that I will discuss is it actually relates a superstring in a flat background to the superstring in what has been called self-dual graviphoton background. Okay, so let me start by giving a review of bosonic T-duality a la Busher. So I'll go a little bit slowly, but this should be completely straightforward. So suppose you have a string theory background in which you have a constant shift symmetry of x. So C is a constant. That means that x, let's say the x1 direction, can only appear with derivatives in the sigma model. So if you just write down the usual sigma model action, so G and B can depend on all the x's except for x1. And if you just separate out the x1 variable, then you get this expression here. So m and n here are everything except for 1. Now, one can write this in a slightly more complicated way by introducing this Lagrange multiplier. So what you do is you replace everywhere dx1 and d bar x1 by these fields a and a bar, which you can think of as Will-Sheet gauge fields. And this Lagrange multiplier here just forces the field strength of this Will-Sheet gauge field to vanish in such a way that when the field strength vanishes, you can replace a and a bar, at least locally, by this dx1 and d bar x1. So I'll say something later about some global obstructions to doing it. Okay, so if one goes in this direction by integrating out the Lagrange multiplier, you just go back to the original action. But now, of course, because AA bar appears in this form here, it's just an auxiliary field which can be integrated out. So if you integrate it out, then instead of getting something like G11 dx1 d bar x1, you get 1 over G11. So that's, now of course, after integrating it out, the action will be expressed in terms of x tilde. So you get x tilde 1 instead of x1, and this should have been also a d bar x tilde 1. That's a typo. So this is the expression you get. So all I've done is replace the x's by x tildes by changing the, instead of integrating out x tilde 1 first, I'm going to integrate out a and a bar first. Okay, now these, let me say something about now this global obstructions to doing this. So in the Busher procedure, if the original x1 variable is non-compact, then, of course, locally, d bar a minus dA bar equals 0 implies that a is dx and a bar is d bar x. But suppose that if you have some non-trivial cycle on the worldsheet and this contour integral is non-vanishing, then, of course, it does not mean that a equals dx and a bar d bar x, because if you plug this in here, you'll find that if it's non-zero, you find that x is not single-valued around when you take it around the non-trivial cycle. Okay, so for genus zero amplitudes or amplitudes on a disk, this is not an issue because we don't have any non-trivial cycles. So for genus zero amplitudes, one can do T-duality for a non-compact x1 variable. But if you have higher genus surfaces, then of course this is not necessarily vanishing, and one can get some global obstruction. So this obstruction can be avoided if you replace x1 by a compact variable instead of a non-compact variable. So now what happens is that when this contour integral is non-vanishing, it just gives the winding number of this compact variable around the cycle. So there's no contradiction as long as you use a compact variable. Okay, so that was just a side comment. So going back to this action we wrote down in terms of x tilde 1. So after T-dualizing, we got this expression. And that implies that the background fields, this G11 and these L's, so just to remind you, L I just used this symbol just to simplify the notation. It's just a sum of G and B, so it has both a symmetric and an antisymmetric part. So it's trivial to write down how these background fields transform just by looking at the terms in the action, and you see that this is how they change. Now, one thing that I did not mention is that you also, of course, have a coupling of phi to the two-dimensional worldsheet curvature. And when you integrate over a and a bar, that produces a Jacobian factor, just coming from the fact that you have G11 a bar. So the Jacobian factor is just the inverse of the determinant of G11, and that can be absorbed because of this Fradkin-Seidlin coupling of the dilaton to worldsheet curvature by shifting the space-time dilaton. Okay, so one feature which will not be true in fermionic T-duality is that there's a minus sign here. So if you change the order of the indices in L, which is related to changing the left-moving and right-moving indices, then you see that the sign implies that the Dirichlet and Neumann boundary conditions are flipped if you have the x1 variable on some D brane. And so that means that bosonic T-duality will change the dimension of the D brane. Okay, so these are just obvious things. Maybe if you haven't seen this treatment using Busher, it might be less slightly new. So now we're going to do the same thing if you have some fermionic variable. Now, if you have space-time supersymmetric sigma models, so we can't do this if the fermionic variable is like in RNS because that's not the worldsheet scalar. But if you look at space-time supersymmetric sigma models, for example, the Green-Schwarz sigma model, or either this pure spinor or hybrid versions, or really any space-time supersymmetric sigma model, you have these fermionic scalars on the worldsheet, fermionic space-time spinors, which are worldsheet scalars, which can be encoded together with the x's by this variable y. So for example, for type 2, if you want to describe the sigma model for the type 2 superstring, capital Y can either be the x's or the thetas. And capital M, it would be either the vector index small m or the spinor index. Okay, so for type 2 superstring, m goes from 0 to 9 and mu goes from 1 to 32. If you're doing heterotic, mu would go from 1 to 16. Okay, so this is the Green-Schwarz sigma model, just the first term here. And if you want to quantize it, it turns out you need to introduce couplings to fermionic momentum and also to ghosts. And those come in this pure spinor and hybrid formalism. But actually, the fermionic T-duality can be understood already just using the Green-Schwarz sigma model. Okay, so if you're unfamiliar with this kind of superfield notation, So these are space-time superfields. They include all the component fields of supergravity. And the way they do that is they satisfy some torsion and curvature constraints. So if you construct torsions and curvatures out of G and B, you find you don't allow them all to be independent. You set some of them to be zero. And some of those are equations of motion, some of those are conventional constraints. But after you do this, you find that G and B, capital G and capital B, can be expressed in terms of the usual supergravity field. So for example, if you expand near flat space and you take the vector indices for capital G, you find the theta equals 0 component is just the usual metric, then you get the gravitino, then you get Ramon-Ramon field strength, and then you get derivatives of these fields. Okay, so now we put this into a sigma model. So we're going to make the same kind of assumption as we did for the x's. Suppose that the background superfields are chosen in such a way that they're invariant under this constant shift of theta 1. So instead of a constant shift of x1, now it's a constant shift of theta 1, so Xi is fermionic, which means, of course, that theta 1 can only appear with derivatives in the action. Now, of course, if you do this and anti-commute with itself, you get 0, just because a constant shift anti-commutes with itself, which means that this type of isometry has to be satisfy this type of condition. So that's why it's called an abelian supersymmetry. So it's supersymmetry just because it's a fermionic isometry. Okay, so if we start with this action and do the same expansion as before, so now capital L will be just defined to be the sum of capital G and capital B. Then we separate out the term when mu is equal to 1. So mu is equal to 1 is this component of theta. Now you find the first difference is that because theta is anti-commuting, instead of coupling to G11, now it couples to B11, because this is antisymmetric in Z and Z bar. So that's the first difference. You have B11 separated out. So we'll assume that capital B11 is non-vanishing. And then you have these extra terms. So this again has a part which is symmetric and part which is antisymmetric. And remember, the 1 is always refers to the mu index and not the small n index. Okay, and then you get a general term which is independent of theta 1. Now we're going to do the same procedure. We add this Lagrange multiplier term. So the Lagrange multiplier term enforces that now it's a fermionic gauge field. So A and A bar script A and script A bar are fermionic. And if the two-dimensional field strength vanishes, then locally you can replace it by the derivative of theta 1 and d of theta 1 and d bar theta 1 for some theta 1. So you can go from here to here just by integrating out theta tilde 1 and solving the equation of motion for A and A bar. Or you can go in this direction. Again, if B11 is non-vanishing, you integrate out A and A bar and you get this action. So some of the signs are slightly different, but it's essentially the same procedure as we did in the bosonic case. We just have to, of course, be careful that some of the variables are now anti-commuting. Okay, so again, I'm going to make a side comment as we did before. So in space-time supersymmetric sigma models, theta 1 is usually associated to be single-valued if I take it around any non-trivial cycle. So it has the same properties like a non-compact x1 variable. There's no winding modes when you take it around. So that means this condition, although locally you can always write it in this form, there could be a global obstruction if this contour integral is non-vanishing. So if you have a non-trivial cycle C, and you take this contour integral around C, if it's non-vanishing, then it means that there's no single-valued theta 1 which satisfies this. So again, if one is just looking at tree amplitudes, genus 0 amplitudes, where there are no non-trivial cycles, this is not an issue. So there's no problem with doing this fermionic T-duality if you're concentrating on genus 0 amplitudes. But on higher genus surfaces, this is not a T-duality, this is not a symmetry. So you can't do this just because you can have obstructions. Now you can ask if there's some analog of making X compact in this case, and in fact there is, but it's slightly strange. So to make fermionic T-duality a symmetry at higher genus surfaces, you would have to introduce a multi-valued variable. So it's not periodic or anti-periodic, it's multi-valued in the sense that if you take it around a non-trivial cycle, it changes by a constant amount. So for every non-trivial cycle, you'll have an extra fermionic constant or extra fermionic zero mode. And if you want to make sense out of this T-duality, you would have to integrate over all these extra fermionic zero modes when you do the functional integral. So normally one doesn't do this in a sigma model, so that's why fermionic T-duality is only a symmetry for tree amplitudes in string. Okay, so going back to the action. So after doing this T-duality, we found this new sigma model action. So we integrated out A and A bar instead of integrating out the Lagrange multiplier. And this tells me how the background superfields transform. So they transform in this way, where again, L is the sum of G and B. So capital B11 transforms in a similar way to the way G11 transformed in the bosonic case. It just becomes 1 over it. So we have to assume it's non-vanishing, and there's a minus sign here. And there's a plus sign here. So that was also different from the bosonic case. But other than that, it's essentially the same form. Now, because script A and script A bar are fermionic gauge fields, it means when you integrate them out, instead of getting the Jacobian factor of determinant of G11 to the minus 1, now you get the determinant of B11 to the plus 1, just because they're fermionic. So this, of course, can be absorbed as before by shifting the dilaton. So this, because the dilaton again couples to the two-dimensional Wilczek curvature, but now you get this type of shift. So it depends on B11 and with a different sign. Okay, so the plus sign here implies that unlike in bosonic T-duality, where Dirichlet and Neumann boundary conditions for x1 are flipped, now the Dirichlet and Neumann boundary conditions for theta1 variable are not flipped. So if it were flipped, maybe you would think that somehow the fermionic directions are changed. The fermionic dimension of the d-brane is changed, but in any case, fermionic T-duality does not affect the dimension of the d-brane. So this is another difference between bosonic and fermionic T-duality. So for example, if one thinks about the ADS case, the bosonic T-duality, of course, has changed the D3 brane to a D-1 brane, but the fermionic T-duality doesn't change it anymore. So you're left with still the D-1 brane. Okay, so what I told you before is how these superfields transform. So these capital G and capital B. But of course, one really wants to know is how the component fields transform. So it's not so easy to do. And in fact, the most convenient way to find out how the component fields transform was worked out for bosonic T-duality in these supersymmetric, space-time supersymmetric signal models by Benicio, Polycoster, and Truss using the pure spinor formulas. I'm not going to go into the details of this, but essentially what you do is you add terms to the Green-Schwarz sigma model action, which make it BRST invariant. And the terms you add depend precisely on the Ramon-Drummond field strength. So you can read off from the way the sigma model in the pure spinor formalism transforms into T-duality. You can read off how the Ramon-Drummond field strength. The Green-Schwarz sigma model, you have to do a little bit of work. So it's in the paper, but I'm just going to give the result here. So if you define capital C to be the theta equals 0 component of B11, so this is just some bosonic component field, because although 1 and 1 are fermionic indices, if you have 2 of them, of course, it's a bosonic object. So capital C is just some bosonic object, which I assume to be non-vanishing. Then the metric you find does not transform under fermionic T-duality. Neither does the small b field, the usual Kalb-Ramon field. The dilaton transforms in precisely the way I discussed earlier because of the Jacobian coming from integrating out A and A bar. And the Ramon-Drummond field strength transforms in this way, which looks slightly complicated. So capital F is the Ramon-Drummond field strength written in bispinor notation. So bispinor notation just means you can expand. So for type 2b, this is the 1 form, the 3 form, and 5 form. And I'm using bispinor notation where alpha and beta hat go from 1 to 16. So these are just the n equals 2, d equals 10 spinor indices. So this is, of course, for type 2. You could also do heterotic if you liked. Of course, then there would not be any Ramon-Drummond fields. Okay, so you find that this value shifts. And it shifts by something which is related to the killing spinor associated with the abelian isometry. So you have a fermionic abelian isometry. That means that the background has a supersymmetry which is associated to this killing spinor. So the killing spinor has indices with respect to both alpha and beta hat, but of course there's only one killing spinor. So these are just the 32 components of the killing spinor. And this is the same C that appeared here. So this is the inverse of C. Now, because it's an abelian supersymmetry, that's because the shift isometry, of course, anticommutes with itself. That means that the killing spinor satisfies this condition. So, of course, in general, you could get some translation here, but because it's abelian, it means that the sum of these two terms has to vanish. Now, there's another constraint coming from the torsion constraint. So if you try to solve the torsion constraint with this value of B11, you find that there's another condition satisfied with the killing spinor, which relates it to C. So capital C is not an independent field, but the derivative of it is related, space-time derivative of it is related to this combination. So the difference of of epsilon, gamma, epsilon, and epsilon hat, gamma, epsilon hat. Okay, so using this relation that I just told you between the space-time derivative of C and these killing spinors, one can easily check that the transformed background field, so after doing the fermionic T-duality, that they satisfy the supergravity equations of motion, of course, assuming that the original background satisfies. And they're also invariant under a new abelian supersymmetry, which is described by a slightly different killing spinor. So instead of being just epsilon alpha and epsilon alpha hat, now it's epsilon alpha over C and epsilon alpha hat over C. So if you use this value of the killing spinor, and you use these values of the background field, then you find that when you do a supersymmetry transformation, the background field, the fermions don't transform, assuming that the fermions didn't transform using these background fields, using the original background fields and using the original killing spinor. So that's maybe a 5-line computation. Okay, now, as I mentioned already, the space-time derivative of C is related to this difference of epsilon gamma and epsilon gamma, epsilon hat gamma, epsilon hat, but the constant mode of C is unconstrained. So an easy way to see that it's unconstrained is if you set B11 to be constant and just look at this term in the sigma model action, then you can see that it can be written as a total derivative. So just by pulling some of the D's and D bars off, and then if B11 is constant, you can pull this to the other side. So assuming that surface terms can be ignored, the constant mode of C is unconstrained. Okay, so now let me give some examples. So that's the summary of fermionic T-duality. So the first example is, suppose it's a flat background. So I'll do a little bit better. Suppose it's D equals 4 Minkowski plus some general Calabi-Yau threefold. The Calabi-Yau threefold won't play any role, but I'm only going to do this because it's relevant for topological string applications. Okay, so for this case here, instead of using Green-Schwarz sigma model, it's convenient to use the D equals 4 hybrid formalism. That's very well suited for describing this type of background. And if you have flat D equals 4 Minkowski, the sigma model action in this background is quadratic, so it's trivial to quantize. You have a canonical momentum for P, a canonical momentum for theta, which I'm calling P, so this is a fermionic variable. And these are just the n equals 2, D equals 4 theta. So you have theta A dot, and you also, these are left moving, and the right moving ones are theta hat A and theta hat A dot. And then you have a action for the Calabi-Yau sector, which in the hybrid formalism decouples from this 4-dimensional sector. Okay, so it's convenient to choose a chiral representation for the n equals 2, D equals 4 supersymmetry, in which the chiral supersymmetry generators are just dd theta and dd theta hat. Once you do that, then these, of course, are abelian supersymmetries because the square of these are 0, which means we can now T-dualize with respect to theta A and theta hat A. So we're not going to do anything to the anti-chiral theta. Now, in order to T-dualize, we need some non-vanishing value for B11. Now, that can be obtained just by adding a trivial surface term. So if capital C is constant, this is, of course, a total derivative for the same reason I just mentioned. So you can add it, and as long as you can ignore surface terms, it has no effect. So in this case, I'm going to choose C, A, B to be. So A and B, remember, are just, it's just a chiral two-component index. So this is, if C is symmetric, this is just a self-dual tensor. So this is the term I'm going to add. And after T-dualization, it's easy to see that what you get is you get an extra coupling of PP hat. So you just proceed you do the same Busher procedure as before. You add this Lagrange multiplier, you integrate out the Wiltshire gauge fields, and you find that this extra term is generated. So this term is precisely the term you add if you want to describe the self-dual graviphoton background using the hybrid formalism, where FAB is just the self-dual graviphoton field strength. So it's proportional to the inverse of C. And this, of course, was used in topological strings and also for describing non-anticommutative gauge theories by Agorian-Vaff and also by Seiberg. Now, as I mentioned earlier, this fermionic T-duality is a valid symmetry for genus 0 amplitudes, but on higher genus surfaces, these two backgrounds are not equivalent, and the reason is because of these extra fermionic zero modes that I mentioned that have to be added. So at least for tree amplitudes, flat backgrounds and self-dual graviphoton backgrounds are very similar, but for loop amplitude, there are extra features. Okay, now let me go to the case which we're most interested in, which is this ADS 5 times S5 background. So we can describe it using a sigma model. So Matthias Zeitlin constructed these currents. So this is just the Green-Schwarz sigma model. You construct these left invariant currents constructed out of this G, taking values in the ADS 5 times S5 coset, PSU224 over SO41 times SO5. And I use a notation where capital A can either be a vector index or left moving or right moving spinor index, or if you like, n equals 2 spinor index. And then if you just write down the Green-Schwarz sigma model in terms of these left invariant currents, you have the following simple form. This comes from GMN, this comes from BMN. In this case, B11 is non-vanishing, so you don't have to add any non-trivial surface term. This action is, of course, invariant under the global PSU224 isometries, which come from acting on the left by this constant matrix PSU224. And now it's convenient to choose a parameterization of G such that the 4 translations of Minkowski space PM and the 8 chiral supersymmetries, so this PSU224, of course, contains the n equals 4, d equals 4 superconformal algebra, and 8 of those generators are just the chiral space-time supersymmetries. So you can choose a parameterization such that these translations in 8 chiral supersymmetries just act by a constant shift. So these are, of course, the same bosonic shifts we had in bosonic T-duality, and these are just the fermionic shifts we had in fermionic T-duality. Now we have 4 of these and 8 of these, but we can just do them one by one and compute how they act on the sigma model. So, of course, these shift isometries leave the sigma model invariant just because the model is invariant under all the PSU224 isometries. Okay, so after T-dualizing the XM variables, you find the ADS5 metric is invariant for the same reason I discussed before. This was first noticed by Calvin and Zeitlin. And the Ramon-Ramon field strength and dilaton transform in the same way as I said before. The phi form changes to the 1 form, and the phi is no longer constant, but now it picks up this dependence on y coming from the T-duality. Now, if one also T-dualizes with respect to the 8 fermionic variables, one finds that, of course, the metric doesn't change anymore, but the dilaton now picks up a contribution coming from the fermionic T-duality, which, because of the opposite sign, precisely cancels the transformation coming from the bosonic T-duality. Similarly, the Ramon-Ramon field strength picks up this term here, and if you work out what C inverse is and what these killing spinors are, you find that this term here precisely cancels the change from the phi form to the 1 form, and returns the Ramon-Ramon field strength to the phi form. So the ADS 5 times S5 background is invariant, at least if you want to compute amplitudes on a sphere or on a disk. So, of course, amplitudes on a disk are related to planar Super-Yang-Mills amplitudes, as I'm sure Fernando Alde will discuss. So this relates planar Super-Yang-Mills amplitudes in Wilson line correlation functions, not just at large truth coupling, but at arbitrary truth coupling. At least if one ignores this polarization-dependent factor, which I won't say anything about here. Okay, now in acting on the T-dualized variables, you can ask what happens to the PSU224 transformations. So P and Q become trivial. That's just because they act by shift isometries on X and theta. So on X tilde and theta tilde, they don't do anything. Now, and also on the other variables, they don't do anything. The conformal and chiral superconformal boosts become non-local. So if you just ask what happens to the original PSU224 transformations, you find that these transformations don't act in a nice way on the dual variables, on the T-dualized variables, but these do. So it turns out the dilatation transformation just goes to minus the dilatation. That's just because y prime has is dependent on proportional to 1 over y. The anti-chiral superconformal and supersymmetry transformations change roles, but these transformations here are new. So of course, after doing fermionic and bosonic T-duality, you still have an ADS 5 times S5 background, which is PSU24 invariant, but these generators of the new PSU224 were not generators of the old ones. So these are the new dual superconformal transformations. And the old ones turn out to form this subgroup of PSU224. Okay, so this dual superconformal group, of course, as will be described in the next talk, was simultaneously described by other authors. Okay, so let me go to conclusion. So the superstring backgrounds with abelian supersymmetry, if you have an abelian supersymmetry, you can relate it by fermionic T-duality to another superstring background, where this is the way the fields transform. So this is generic for any superstring background within abelian supersymmetry, and these are the properties of the killing spinor. So they're related to this capital C, which appears in the fermionic T-duality. So for superstring T amplitudes, the background after doing T-duality and before is equivalent, so again, only for tree amplitudes. And as I already mentioned, under fermionic T-duality, if you just start with flat T equals 4 Minkowski background, you end up with a self-dual graviphoton background. And if you start with the ADS 5 times S5 background, and you choose to T-dualize these 4 X's and these 8 thetas, you end up with the same background. Okay, so let me discuss applications now. So these are applications which have already been found. So it explains this dual superconformal symmetry for perturbative super Yang-Mills amplitudes, which will be described in the next talk. It can also be used to relate non-local conserved currents of the ADS 5 times S5 sigma model with these dual superconformal generators. So you have these new superconformal generators that I discussed, which are not in the original ones. And they turn out to be related to these non-local conserved currents. So this was described by these authors in 2 papers. And except for this unresolved issue of polarization dependence, this extends the Aldate-Maldacena result relating planar Yang-Mills amplitudes and Wilson line correlation functions at arbitrary 't Hooft coupling. So let me just quickly say some possible future applications. So of course, one possible application is to use this fermionic T-duality to learn about the self-dual graviphoton background. Another possible application is to see if there are some similar invariances of other ADS backgrounds, ADS 3 times S3, for example. One more speculative application is to try to use fermionic T-duality to enlarge the U-duality group of supergravity backgrounds. So this, of course, is usually taken to be some bosonic group, which involves T-dualities and S-dualities. Now you have a new type of fermionic T-duality, so that may enlarge this group to a supergroup. Of course, this is only for genus 0 amplitudes, but still this may be useful. And one possible application is in these E10 or E11 models, which have been discussed by various authors, but mainly Nikolai and collaborators and Weston collaborating. These E10 and E11 models may be naturally extended to some supergroup models if you include fermionic T-duality. And there might be a more natural way than what has been done up to now for these models for understanding the fermionic supergravity field. So there's a very nice way to understand bosonic supergravity field as being related to the bosonic root lattice of these models. And maybe if you have fermionic generators, you can similarly understand the fermionic supergravity fields of these models. Okay, so I'll stop there.
Is there any question?
Is it possible to consider the fermionic TST transformation introduced by Newman and Madsen? Fermionic TST transformation.
So you mean in the U-duality, is that?
No. The T-duality in one direction, then to shift in another direction, then to T-duality.
Yes, so you could do it in, that's right, so you could do one after the other. So you could do a T-duality, then do a fermionic T-duality, then do a T-duality in another direction, and then do another fermionic T-duality. I think all of these, you can do one after the other. I'm not sure if that's your question.
Do they commute? I mean,
yeah. So if you have a billion isometries, so you have to start with a billion isometries. So the bosonic shift symmetry has to, of course, commute with the fermionic shift symmetry. So, but because they're constant, I mean, it's just a constant shift, then all of these commute. If you want to ask about some non-abelian supergroup, that I don't know.
Okay, thank you.
any other question?
Does the explanation of the superconformal invariance hold for loop? So from here, is this, or is this limited because you can only do trees?
So first of all, I'm not sure it's even, so trees corresponds to planar super Yang-Mills amplitudes. So up to now, this dual conformal invariance, or superconformal invariance, has only been conjectured for planar super Yang-Mills amplitudes. Now, if there's something that works for non-planar super Yang-Mills amplitudes, I don't know. So if you could say something, then maybe you could say something about this fermionic T-duality for higher genus. But at least at the naive level, there's There's no version of this for non-planar amplitude.
Okay. Yes?
So you can use T-dualities to construct things like non-geometric backgrounds, ordinary ultrasonic T-dualities. So using these sort of T-dualities, could you then use new non-geometric fermionic backgrounds?
I haven't thought about it. I don't.
I think we have to close this part of the session. We thank again the speaker.